It's resistance that destroys the Battlestar.
No, I was like, I'm like, it's kind of fun. I'm like wondering if I could find any more metaphors in that. It's like, oh, I gotta learn more about electricity. I like Star Wars, so
Mm-hmm.
use the Force.
Yes, Luke had a lot of resistance. He could resist the Force.
Resist the Force. Okay.
Okay, so we'll talk about DC power. Similar formula to Ohm's law, but in this case, we want to know about how much power is being delivered or used in a circuit. And power is the rate at which energy is expended or absorbed. Now, the one thing that if you had physics, that energy is never created or destroyed.
First law of thermodynamics.
Energy in the universe is the same.
Yeah.
We can move it around. We can change it from one form to another. You know, we can go from kinetic energy to potential energy and all that kind of stuff. But we don't create it. We don't destroy it. But how we use it, okay, is power. Okay, and that's the rate at which we're doing something with that energy. So a watt of energy is equal to 1 joule per second. Joule is one of those measurements in the CMS system, I guess it is. It's equal to 1 watt second. In other words, 1 watt of power for 1 second. And it's also equal to 1 coulomb volt. We talked about coulombs in the beginning, which was the 6.24 times 10 to the 18th charges. So if you have that many charges and a potential of 1 volt, that's 1 joule of energy. Now, you don't need to remember all those. But it breaks down to that watt is going to be equal to 1 coulomb per second times a volt. And if you remember, we said a coulomb per second was 1 ampere of current. So 1 ampere of current times 1 volt is I times E, which is going to be equal to power in watts. So the formula is going to be P is equal to I times E. And again, we have our little pie chart. This one actually spells pi. We do it the same way. If we want to find power, okay, we just cover that up and it would be current times voltage. If we want to find the current, it would be the power divided by the voltage. And if we want to find the voltage, it would be the power divided by the current. Works just like Ohm's law.
Why don't they use W? If power is wattage, why don't they use W instead of P?
The units are watts. Power is P measured in watts, which is the W.
Got it.
Like R is resistance, but it's measured in ohms. And I is current measured in amperes. We do all that to confuse people.
Absolutely. No problem.
Wait till you get
it's working.
Wait till you get to little j, which is the square root of -1.
Oh, yeah. Okay.
So in this example, I've kind of worked through the algebra to show all the different variations of the power formula. So sometimes, other than the chart, you can use the power is equal to the current squared times the resistance. In that case, you don't know the voltage.
So if I wanted to enhance this pie chart a little bit, I would say, oops, you went on. I would say I would add P power in watts,
Okay.
I current in amps, and E voltage in volts. Would that be
Very
correct?
good. Correct.
I got all the units onto the right part of the pie?
You can add whatever you'd like to it.
Well, I want to make sure that what I'm adding is correct. So powered is in watts. You're
Right.
saying
You're
power
correct.
units is watts
Power would be in watts, current would be in amperes, and the electromotive force would be in voltage.
in volts.
Right.
Okay, so current,
That was the only good one. I
Call it-
like that one. Voltage
it's a
and
little bit,
volts.
yeah.
We tend to call it voltage, but it's really E for electromotive force, which
Okay.
is actually the force that causes the current to flow. It's just like in the physical world, to move something, it takes a force to push it.
That's helpful. Thank you. And there was a fellow named Volt, right? Or Voltage or something.
Volta,
There was
right. He actually
Volta.
invented the first battery.
Like there was an Ampere guy.
There was an ampere guy. There was a Hertz guy.
an ohms guy.
He's got a rental car company.
A Hertz guy, an ohms
Heinrich.
guy.
Heinrich.
We'll talk about a Faraday guy.
Oh, yes, the Faraday cage
Yeah.
and bags and everything else.
Uh-huh. Yeah, a few more of them. Watt is actually after James Watt, who is the Scottish guy that invented the steam engine. So he worked a lot with power, which is why we represent power in watts, because of James Watt.
Honorable.
Okay, so the power formula is the power P is equal to the voltage E times the current I. Or P equals E times I or I times E, doesn't matter.
Starting to get this a little bit.
If we had 13.8 volts, that's an important number because most amateur radio equipment runs on 13.8 volts DC. So you'll see that number a lot. It turns out that that's the nominal voltage for a battery, like a car battery.
Huh.
Not 12?
Well, they call them 12-volt batteries, but when it's fully charged, well, it's around 13.8 volts.
Feeling something else today. Wow.
Could you, Robert, could you take a sec here and the first circuit that we looked at, the very first one, I followed the little arrows and they went neatly through the resistor and around to the negative side, and I got that. But now there's an arrow that goes across the top, and then all of a sudden the other two arrows go the other direction, and so I'm just mystified. I don't know.
Well, the one at the top with the red eye,
I'm good with that one.
okay, that's the current flow.
Right.
This one with the blue E, okay, is the voltage, the electromotive force. So there's a voltage across this resistor because there's current flowing through it. And there's voltage because it's resisting the current, some of the current flow. And it does that by producing an opposing voltage. And in this case, it's a series circuit, but there's only one resistor. So that voltage across the resistor has to be equal to V1 over here.
Oh, God. So I had this simplistic idea that the arrows meant which way the current was flowing.
The I one does, okay. This one is showing the voltage and the direction of the voltage. In other words, it's going to be, if you measured it, it's going to be positive on this end. Oops. And 0 down here.
Down where? Where's your arrow?
At,
down there?
Yeah, here.
Okay.
There it would be 0. And up here,
it's 10.
It's going to measure 13.
Okay.
Oops. It didn't like me clicking.
Too many clicks.
How is the voltage 0 at the bottom? So, and is that 0 is the current, not the current, is the voltage moving up through the resistor? Like, how does it gain?
It's the voltage across it. So if you measured it from this point to this point with a voltmeter, you would see 13.8 volts.
Okay. Why would it be 0 below that, though?
Well, it's just a reference
the current
point.
is flowing around in the same circle that we were used to, right? The current is flowing from the plus sign around the outer edge to back to the negative sign. That's what's happening.
Right. Right.
In the world, the current is flowing around that outer edge of the
current's
box.
going like that.
And then,
Yes.
so
I think what's confusing here is the arrows are going up, but the circuit, the flow is going down.
Right.
And so when it goes to 0,
because they're two different things.
and it continues to go around back to the negative side of the voltage. So is it 0 all the way there until it goes through the battery again, and then it charges up to 13.8 again?
Well, at this point, right here, all of this is 0.
Okay. Yep.
All of this
is 13.8.
13.8.
That makes
sense. So
sense.
the E arrow is indicating that there is an opposition in units of volts.
Right. That's showing you the opposition, which has to be.
That's why it's going in the opposite direction.
Volts.
You smell good.
And it's coming from the resistor.
Right.
All right.
Now, in this example, what we're going to do is find out how many watts that resistor is consuming. Because we have 10 amps of current flowing through it. And we have 13.8 volts. So if we look at the formula, okay, 13.8 volts at 10 amps, there's 138 watts in that resistor. It better be a big resistor.
Which is to say it's stealing away 138 watts.
It's converting that energy into heat. So it would be putting out 138 watts. It would be quite hot.
Because that's how resistors take away energy.
Just think of a 100-watt light bulb. You wouldn't put your finger on it, right?
Ooh. That would hurt.
So over here is just showing the different variations of that formula for power, and they all come out to the same answer, 138 watts. Are you more or less confused?
I think I get this.
Okay.
Well, I think some of it is just in the way that the information is expressed in the figure is not familiar. And so so it actually, the formula is okay, but then I keep trying to relate this diagram to something physical, and that's not really right. it's somewhat right. But it's not really trying to do that. That's what I think.
Okay. Well, the formula is fairly straightforward. So,
Yes, the formula is straightforward. I think it's the up arrows that really blew me away.
okay. Um, so, some example questions, because there will be real ones like these. How much power is delivered by a voltage of 13.8 volts and a current of 20 amperes?
Mhm.
So it would just be the current times the voltage, or 276 watts. So if we have 12 volts and a current of 3 amperes, it's 36 watts. And if we had a voltage of 12 volts and we want to deliver 60 watts, we need to know how much current that would take. So we divide the power by the voltage, and it gives us the amount of current to generate 60 watts at 12 volts.
Gotcha.
Those clear?
Mm-hmm.
Yes.
So, which term describes the rate at which electrical energy is used?
No,
Dissipated.
Charlie.
Charlie.
3 watts.
Charlie sounds good. Electrical power is measured in which of the following units?
Power.
Watts. Bravo.
Okay. It's the rate. Remember, power is the rate of doing work, and it's measured in watts. So what's the formula to calculate power in a DC circuit?
Alpha.
E equals I over E. Whoops. Uh-oh.
Remember your little pie chart.
And I'm trying to remember it. I thought it was I over E, so I'm mystified now.
Power is current times voltage. How much power is delivered by a voltage of 13.8 volts DC and a current of 10 amperes? I think that was an example.
Alpha.
Any guesses?
Oh yeah, alpha.
All right, 138 watts. So how much power delivered by 12 volts and 2.5 amperes? Remember, P is equal to I times E, or E times I, however you prefer.
Hmm. In the pie chart that we use for this, power is on the top, of course.
Right?
Is amps on the lower left part of that pie?
Yep. Yep.
It is?
Yeah.
So I times E equals P.
Mhm.
Correct. So
So I'm trying to
multiply
figure
out.
out where E over I comes from.
You might be thinking
That's
Ohm's law.
Ohm's law. Resistance is equal to E over I.
Say again?
Says that's Ohm's law. Resistance is equal to E over I.
So power is I over E.
Mhm.
Power is equal to I times E.
Okay.
So all we have here, all we know is volts and current. So the regular power formula, P is equal to I times E. So you multiply the two. And the answer is, bravo, 30 watts.
420.
Are we okay with that one?
I'm good.
So how much current is required to deliver 120 watts at a voltage of 12 volts? So here we want to know the current, and we know the power, and we know the voltage. So if you look at the little pie chart, we know P at the top, and we know voltage is 1 on the bottom. So to find the current, we divide
Bravo.
by E.
Mhm. Bravo.
So remember that for power, it's equal to E times I or I times E. They're interchangeable. It doesn't matter which order. If you only know current and resistance, it's going to be the current squared times the resistance. And if you only know the voltage and the resistance, it's going to be the voltage squared divided by the resistance. And you get those by just working out the algebra and using substitution of Ohm's law, and you can come up with those formulas. But as far as the technician exam, you don't really need to know those other two. And we just did that other group of questions. So only one of those questions we just did will be on the exam.
Okey-doke.
So